Epigenetics could be one of the central mechanisms for how early nutrition programs long-term health. Science has demonstrated that a lot of environmental cues acting during and before the first 1,000 days of life have a lasting impact for the rest of the life. One of these environmental cues is nutrition. For example, we know that maternal overweight and obesity markedly increases the child's risk for developing obesity in later ages, and also it increases the risk of associated disorders such as diabetes, coronary heart disease, and stroke. As a result, obesity of the mother during pregnancy will actually reduce the life expectancy of her children. An exciting question, therefore, is what are the mechanisms by which the body can remember over many decades what happened in pregnancy? How is it that 40 to 50 years later the body still knows what the mother has eaten in pregnancy? There are many theories as to what mechanisms could play a role. The body's long-term memory could be mediated through the effects of hormones, by biochemical effects of certain metabolites, and by structural changes of body composition and the function of tissues. In addition, recent research suggests that our body may remember early events by changes to the epigenetic marks of our genes. We are in the century of genetics. The Human Genome Project, probably the largest research project ever performed in the life sciences, aimed to decipher the human genome. When it started, many people expected that once we understand the variation in people's genotypes, we could then explain the variation in phenotype. In other words, knowing the genetic makeup of a person means that you will be able to predict the person's characteristics. However, we've now come to appreciate that biology is actually much more complex. If we detect a patient's mutation in a monogenetic disease such as cystic fibrosis, the mutation alone actually does not allow us to predict the disease course. Similarly, knowing the genotype of a person alone does not allow us to predict all the person's characteristics and all its health risks. Why is it then that we see such a great difference between people, although the inter-individual genetic difference can be very small? It appears that it is more than our genes that determine who we are and what our health and disease outcomes are. Clearly, there's a lot of information to indicate a close interaction between our genes and our environment. In particular, findings show that early environment plays a large part in shaping the phenotype. It is these early environmental cues that allow one genotype to display multiple phenotypes. This process is controlled by epigenetic mechanisms. Epigenetic mechanisms are based on biochemical modifications of the DNA in a stable, heritable manner without changing the underlying DNA sequence. Such epigenetic mechanisms include histone modification and DNA methylation. The methylation of DNA has received a lot of attention because it is now well measurable. Therefore, we have more data on DNA methylation than on the other epigenetic mechanisms. Methyl groups are added to cytosine within DNA. More than 90% of the cytosine phosphatidylguanine or CpG sites are dispersed all around the genome at low density. Less than 10% are clustered in regulatory regions of exons, but here methylation can markedly change gene expression. If these CpG islands are largely unmethylated, then transcription factors can bind to the transcription binding sites and generally induce gene transcription. However, if these CpG islands are highly methylated, the binding of transcription factors is inhibited and genes tend not to be transcribed. Of importance, once a CpG site is methylated, this can be replicated during cell division by the action of a DNA methyltransferase, which makes the changes heritable from one cell generation to the next. DNA methylation is an event that occurs particularly early in life after the ovum has been fertilized by the sperm. much of the methylation that comes from the parent generation is demethylated or erased after the fertilization of the oocyte, which this is then followed by a period of active de novo methylation. Environmental cues, including lifestyle and dietary choices, thereby can change the offspring's physiology and function for a lifetime and modulate long-term health and disease development. Methylation patterns in early development was published by Michaud and co-workers in 1994. The authors looked at agouti mice, which have a genetic trait leading to marked obesity along with the yellow color of the fur. In their experiment, the researchers provided pregnant agouti mice with various methyl donor molecules, such as folic acid, choline, and betaine. They achieved different degrees of methylation in the offspring DNA. Interestingly enough, a high level of DNA methylation led to complete suppression of the agouti phenotype. In other words, the offspring with high methylation of the DNA looked like normal mice with brown fur color and no obesity. Intermediate patterns of methylation resulted in only partial suppression, that is, mottled fur color with some yellow and brown in the fur and intermediate overweight. And low methylation led to the full agouti phenotype, obesity, and yellow color. This experiment actually demonstrates the enormous power of epigenetic gene methylation during critical windows of early development. An example of methylation effects in early development based on normal dietary variations can be observed in bees. The queen of the bees is not genetically determined. She has the same genotype as working bees and only becomes a queen due to different early feeding practices. If during the whole larval stadium of 13 days royal jelly is fed, a queen of the bee develops. However, if royal jelly is only fed during the first 3 days, followed by honey and pollen, then a working bee develops. This has led many people to buy royal jelly at high price with the expectation that mice offer health benefits, but it is actually not the royal jelly that alters the phenotype, but it is the early feeding of honey and pollen which induces DNA methylation. Thereby, genes are suppressed which would otherwise support the development of the queen phenotype. Recently, researchers from the University of Southampton looked at the diet of pregnant women and found that actually the dietary carbohydrate intake during the early phase of pregnancy altered the DNA methylation status at the site of the vitamin E receptor gene. This, in turn, positively predicted body fat deposition at the school age in the offspring. If there was increased methylation of the vitamin A receptor gene at the time of birth, then the children at the age of 6 and 9 years respectively had higher levels of body fat deposition. This exciting finding demonstrates a close link between neonatal epigenetics and later disease risk. Here at LMU Munich, we studied the effects of maternal smoking on the child's epigenetics. We know that if the mother smokes during pregnancy, the average birth weight is reduced by about 300 grams. From other studies, we also know that there's a linear positive relationship between birth weight and later obesity risk. Therefore, one might suspect that a child will be protected against later obesity if the mother smokes and the birth weight is reduced. However, in fact, the opposite is the case. We and many other investigators found that the children of women who smoke in pregnancy, particularly if they smoke in early pregnancy, carry a markedly increased risk of overweight and obesity later in life.